Good morning, afternoon, evening, whenever you happen to be watching this. It is the weekend, so I trust you're all staying safe and staying legal. What I'm going to do in this video is kind of take you through what I would normally talk about with you guys as a class if we were actually in school. So here we go. Okay, if you think back to Friday at the end of class, we briefly talked about the electromagnetic spectrum, and we talked specifically about visible light, which is what we can see. Our spectrum that we're used to seeing is the red, orange, yellow, green, blue, indigo, violet. I did also talk about the radio waves, which are very, very long, could be several hundred meters long. And then as we move to the right, the waves get smaller and smaller. The ultraviolet waves can penetrate our skin and affect our skin cells. The X-rays are even smaller. They make it through our skin, and they can. That's why we get X-rays. They can see broken bones and stuff like that. And then even smaller, we have gamma rays. Again, we can only see visible light. That's what our eyes can see. But stars and other things are emitting light all along the spectrum. They're emitting infrared light. They're emitting gamma rays, all sorts of stuff. But right now, we're just going to focus on the infrared light. The other thing I mentioned briefly was the idea that different gases emit light at different wavelengths along that spectrum. So for example, a hydrogen gas will emit light at certain wavelengths. Helium gas, oxygen, carbon, all these different elements are emitting energy, I should say, at different wavelengths. At the same time, they will absorb light at the very same wavelengths in which they are emitting them. So sort of an emission spectrum and a absorption spectrum will kind of be the opposite of each other. So this here is just sort of a made-up example where we have emission lines here, here, and here, and absorption lines correspond to them. These are handy because when we study stars, we can actually tell what's in them. You know, the sun, we've never been to the sun. It's not like we can take a sample of the sun and take it back to a lab and analyze it and see that it has helium and hydrogen and that sort of stuff. What we do is look at the emission lines and the absorption lines from the sun to understand that our sun is basically a giant ball of burning hydrogen. Other stars we can see, some might be burning helium, some could be burning carbon or oxygen, maybe even iron, just depending on how big they are, how hot they are, or where they are in their life cycle. So the first thing that's nice about understanding the electromagnetic spectrum and understanding light is we can tell what stars are made of. Here's another quick example, just some actual absorption spectrums and emission spectrums. This is what sodium looks like. This is the absorption spectrum for mercury. This is the absorption spectrum for lithium. And kind of we get to see that nice mirror effect. This is the emission spectrum of lithium. So this is where lithium is emitting gases actually. So question I'll pose is, or not a question really, but a statement I'll say, there's a way that we can use this information to tell whether a star is moving towards us or away from us. And that phenomenon is called the Doppler effect. The Doppler effect, my guess you guys have heard of, maybe watching the weather reports to say we have Doppler 3D radar, that sort of stuff. The reason it has that name is because they're using the Doppler effect in their radars to gather information about clouds and weather systems. We are going to talk about the Doppler effect from the standpoint of light waves. What are light waves doing that are reaching us from these different stars? To explain the Doppler effect, it's somewhat complicated, but I think once you see it and hear it in action, it'll make a whole lot of sense. To help explain the Doppler effect, I'm going to enlist my good friend Sheldon Cooper from the Big Bang Theory. Here he goes explaining the Doppler effect.
Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
So he said kind of a mouthful there. Um, he's going to go on and give a brief example of what the Doppler effect is. And I'm sure when he gives his example, you guys will have an idea and probably experienced it at some point in your life.
Oh, sure, I see it now. The Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay. See? People get it.
Hi.
Hi. Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
So the definition, the actual literal definition of the Doppler effect, the apparent change in the frequency of a wave caused by a change in the actual source of the wave or the observer. So he gave his little audio effect to demonstrate the Doppler effect, that sort of meow sound. If you ever watch like NASCAR or something on TV, you'll see that every time the cars pass the microphone. That is the Doppler effect. I think a good way to demonstrate it as well is to actually see what it looks like. You know, we can't see sound waves, but we can make visual representation of sound waves. So here in this situation, we have two different people. Here's a green guy, here's the red guy. The red person is the source of the sound. He can be singing, humming, who knows what he's doing, but he is the one that's giving off the sound. So when they start making sound, that frequency is going to be constant. All right? There's the same amount of space between each one of these waves. The person who hears the sound is getting hit by these sound waves at exactly the same interval. There's the same amount of time between this sound wave, between this sound wave, between this sound wave. That is, that is when you hear a constant sound. However, when we take a similar scenario but change it a little bit, here we have the person in red is still giving off the sound, but we have two different people observing that sound. We have someone who's behind him and someone who's in front of him, and we set the person making the sound in motion. We see something different happening. We see for the person that is behind the source of motion, the person who's being moved away from, the frequency changes a little bit. The distance between each one of these sound waves and the time between each one of these sound waves hitting the listener is increased. All right, so the frequency is slowed, or decreased. The frequency is slowed down. There's less frequency. However, the person in front of the sound is getting hit by waves more frequently. There's less space between each wave, so there's less time between each wave that hits him. So the person behind is going to hear a different sound, a different pitch sound than the person in front. Here we have a higher frequency. Here we have a lower frequency. Another example of what that actually sounds like is we could use a oncoming car honking their horn. So as that car passed, it was pretty clear to hear the change in frequency from when we were in front of the sound to when we were behind the sound. As the car was approaching, we were in the position of this blue person right here. The frequency was greater, so the pitch of the horn was higher. After the car passed us, we played the part of the green person here. The frequency had been decreased, so the pitch was lower. Again, here's high frequency, high pitch, low frequency, low pitch. Let's just listen to it one more time. again, it's pretty clear to hear that change. And that change is the Doppler effect. That's the difference that we hear, the Doppler effect. Now the question is, how can we use our knowledge of the Doppler effect here, where we see the apparent change in the frequency of a wave caused by the source of the wave or a change in the listener. How can we combine the knowledge of the Doppler effect with our knowledge of emission and absorption lines? So here we see, the gas coming from the planets or coming from the different stars. Here we have the Doppler effect. Well, here's what astronomers are able to do. If we take the two different absorption spectrums. Here's on the bottom we have an absorption spectrum that is from a star that is not moving, that is moving at the same rate at which Earth is moving. Kind of like if we were driving next to them side by side on a highway. If you're driving on a highway at 70 miles an hour and a car is driving right next to you at 70 miles an hour, it almost looks like that car is not moving. That's because you're both moving at the same speed. So that is this absorption spectrum right here. The one on top here is an absorption spectrum of a star that is going to be moving either towards or away from us. So here's what happens when we look at absorption spectrums from stars that are moving towards or away from us. If it's moving away from us, we see those absorption spectrums shifted a little bit. And it's no accident why in a way a star that's moving away from us is shifted in one direction and a star that is moving towards us is shifted in the opposite direction. The reason being is, let's go back and look at our electromagnetic spectrum. Here's our visible light. The red end of the spectrum is longer wavelengths. The further we go to the left on this spectrum, the wavelengths are getting longer and longer. So light waves, red light waves, are longer wavelengths. On the blue end of a visible light, the wavelengths are shorter. So down here we have shorter wavelengths anytime you see blue light. So if we go back and look at our Doppler effect here, if we have a star that's moving away from us, when it's moving away from us, we are essentially this person in green right here. So we're getting hit by wavelengths that are longer in wavelengths and lower in frequency. And so that is why it is shifted towards the red end. Again, here's what it would look like if it's stationary. As it's moving away from us, it gets shifted towards the red, and that is because the red wavelengths are longer. We are that person here in green where they're experiencing red wavelengths, or longer wavelengths, higher or lower frequency. If the star is shifted, or the star is moving towards us, it's the opposite. It's moving towards us, so we are the person in blue right here. We have a higher frequency and a shorter wavelength, and that is because, again, on our visible light spectrum here, the blue wavelengths are shorter. So again, if it's moving really, if it's moving just very slowly towards us, it'll be a barely noticeable shift. The faster it's moving towards us, the more obvious the shift will be, to the point where, it almost looks like we're looking at different spectrums. If it's moving away from us just barely, then we have a situation, then we have just a very barely noticeable shift towards the red end. If it's moving away from us very quickly, then we have a much greater shift towards the red end. And so this is called the Doppler shift, based on the Doppler effect. So astronomers and scientists will look at all these different stars and get information from stars and see whether they are red shifted or blue shifted, and that allows them to see whether they're moving towards us or away from us. So that is kind of the point of what I wanted to get across today in this e-learning session. You'll notice in the announcements section in our astronomy group on My Big Campus, where you found this video obviously, so you noticed it, but there is a short writing prompt that I'd like you to respond to. You can email me your responses. If you're having trouble with email or whatever, you can write it out and just bring it with you when you come to class on Monday, or drop it off in my room at some point on Monday. But the prompt should be fairly straightforward. If you do have any questions, feel free to email me at any time. Like I said, I will be checking my email pretty much at any point throughout the day, all day Saturday, all day Sunday. Probably the only time that I won't be at my computer or within reach of my computer will be Saturday evening. But at any other time, email me if you have any questions. I hope what I put together was clear and made sense to you. If not, that is why email exists. I hope the e-learning goes well for you. Enjoy the rest of your weekend, and I will see you all on Monday.